Okay, we're on problem number 9, and we have an illustration here. We can see where there's this big curve. It's a rocket that's launched upward, and it says when a rocket is launched upward, how high it goes depends on its height and speed at burnout, the moment at which its propellant is used up. Now, a formula for this is h is equal to a plus r squared divided by 20. In which h is how high the rocket goes up in meters, a is its height at burnout in meters, and r is its speed at burnout in meters per second. Okay, so you see a lot of complexity to this, but the simplicity is right in front of you when you draw it. Okay, if I were to just give you these words without drawing it, it would be very confusing. So let's go ahead and draw our illustration here. And we just have the ground, let's just say. It's good to start with the ground. And then we have this, the path of the rocket as they drew it. Okay. And then we have the measurement of the height. Okay, this is going to be h. Okay, so we have h, and then we have a. Now we're going to talk about these, and that way we can better understand what exactly it is they're telling us here. We have h is how high the rocket goes. So this is the top of the path. That's the highest height of the rocket, and that's at burnout. Remember, there's a propellant. There's something that's propelling this rocket to go upward. It's going against gravity. There's a force. So you can imagine, just picture a big rocket ship. Obviously, if you were just to launch it, it's going to eventually run out of propellant. And if that's the case, then if it was not, if it had not escaped our atmosphere and our gravity, then it would come right back down to Earth. So a is the height at burnout in meters. So what's particular about this, and again, I should have drawn this probably a little better. Let me just clean that up because I want the path to really illustrate. I should have drawn this with more dotted lines. And the reason is because the solid line is where the propellant stops. Okay, now this is just the path, and you could just see the dotted lines, meaning it's just now going beyond the propellant, because once the propellant ran out, it still had momentum, right? But eventually what happens is that the force of gravity is going to slow it down, and it's going to reach its apex, let's call it, that's the top, and then it's going to start coming back down at a certain rate as well. So a is the height right here. This is where the propellant ran out, okay? Now you notice it didn't just come straight back down to Earth. Why? Because everything that I just said. It had momentum. Now, use this formula to find out how high a rocket goes if it is 40 meters high at burnout and traveling at a speed of 30 meters per second. Now, this all sounds somewhat complicated, but let's go look at our formula here. Let's put it down here at the top. I'd say this is probably the best place to put it right now. And h is equal to a plus r squared divided by 20. Now let's just take a look at this again. A is the that's the height when we run out of propellant, okay? And we're going to add the speed, okay, r, the speed at that moment, at the speed at which it hits burnout, because its speed was 0 when it was on the ground, and I'm sure it was just increasing in speed, but then pop, it ran out of gas. So now it's just continuing, and that moment is r. That's the speed at that moment, and they're squaring it and dividing it by 20. Now you might say, well, why do they do that? Well, it's just science, okay? This is a formula that they're given to us, and this is something that scientists have determined, let's just say, if you were able to determine what the speed was. Now, there's probably a whole lot more that goes into this, okay? So let's just understand that we've been given a formula, and now we need to work with that formula. Somebody says, this formula, it works. Let's use it. Okay. Now, we're going to sit here and we're going to try to use this formula to find out how high a rocket goes if it's 40 meters high at burnout. Okay, so what is 40 meters high at burnout? Well, that's the H. Okay, I'm sorry, that's the A over here. It was A. It was A is the height at burnout. So that's the A at burnout. And again, we can get very creative with our letters. In fact, we could use HB. Okay, all right. That would be burnout. You'll be using a lot of different variables, but we're just going to go with what they've given us, and let's put that number in. It's 40 meters. Okay, so we're dealing with meters. Now, technically, we should be putting in these things, but because we know that things are being measured in meters per second, the speed, then we can go ahead without that. We'll just go ahead and use no units, because it does get a little confusing with our math. But as you go along in science, you're really going to have to do it, particularly when it comes to conversion of these units, because you may be measuring something else in, say, kilometers per second. Okay, so then it would require a certain amount of conversion. But we're not going to confuse you with that. We're just going to stick you here with the simple puzzle. 40 plus, now it says that it was traveling at a speed of 30 meters per second. 30 meters per second. I'm sorry, I should have put H here. Now, that's the speed R right here. All right, that's the speed at this point. And so we're going to do 30 squared, and we're going to divide that all by 20. Okay, so now you can see it's a pretty heavy duty formula. It's going to have some math that goes with it, and we're going to have to sit there and figure out. So I'll just break out my calculator, and we're going to sit here and do the math. We're going to say 30 squared. 30 squared would just simply be 30 times 30, or if you have a nice scientific calculator, you can do 30 squared, and we'll find out that that's 900. Okay, now why did I do this first? Well, order of operations. I can't do anything until I get rid of these exponents. So I have 40 plus 900 divided by 20. Now, if you just kept that 900 on your calculator, you can go ahead and divide that by 20, and you're going to find out that 900 divided by 20 is 45. Okay, and now the height is equal to 40 plus 40. Oh, I'm sorry, we already did that part. It's equal to 85. 40 plus 45 is 85, and it usually is. Okay, so what does this tell us? Now just think again. A is this height. That's A. It was at 40, or excuse me, I'm using the word feet. It's in meters. So I'm corrected. And there's a big difference between a foot and a meter, because a meter we already spoke of as being 3 times greater, the meter 3 times greater than, say, a foot, because it's closer to like a yard. So anyway, we have here 40, which is where we ran out of propellant, but it kept going another 45 meters. And by getting up to that height, we're able to add these two, and we're able to determine that that is the height, the highest height, before it starts running back down. Okay, that's the height. That's the highest point. Remember, it says here, when a rocket is launched upward, how high it goes depends on its height and speed at burnout. So this was the height at burnout, and this was the speed, and how it affected it was it gave it another 45 meters, which meant the height was 85 meters. Now we're also going to be given here, solve this formula for A in terms of H and R. Okay, so you know how to do that. All we would do is move things from the left to the right, and this one's pretty easy. Let's see, A plus R squared over 20. Okay, and that's equal to H. Now why did we do that? Well, we simply took that formula and we switched it around, and we put the A, and then we say A is equal to, and what we're going to do is we're going to subtract this entire fraction. Okay, so we're just going to subtract it now, and we're going to get H is equal to, or excuse me, A is equal to H minus R squared over 20. So we're moving the entire fraction over to the right, and we solve this for A. Now when we read C, we'll see why we did B. Is because if a rocket is traveling 40 meters per second at burnout, okay, so we have the A, right? Or I'm sorry, we have the R. That's the speed. All right, we have an R. Just going to go up here to our diagram. And um, what would its height at burnout have to be in order for the rocket to reach a height of 150 meters? So it would have to reach this height of h, okay? So it looks like we have the h and we have the r. We can find out what the a is. So that's what they're asking. They're saying if a rocket is traveling 40 meters per second at burnout, what would its height at burnout have to be, which is basically right here. It's A. So we already solved it. So why don't we I'm going to swing this all the way up to here, and let's figure that out. We have A is equal to h minus r squared over 20. And we're told that h is 150 meters, is it not? And we're told that the speed was 40 meters per second. So that would be 40 squared, and that would be divided by 20. So we would again have to go to our calculator and do 40 squared, and that would be 1600. So A is equal to 150 minus 1600 divided by 20. Now we divide that by 20, and it's 80, so A is equal to 150 minus 80. And that means A is equal to 70 meters, meaning that the burnout would have had to have happened at 70 meters. Right here it would have been 70 meters, and if it were traveling at this R rate, all right, all the way up to the top of 150, we knew what the h was, we knew what the r was, we were trying to determine what the a was, and we simply used this formula down here where we solved for a. Okay, so that is problem number 9.